Hello students, welcome to Sops's classes. We were discussing in the previous class regarding the linear dependence and independence of vectors. We are done with the definition of linear dependence and independence of vectors. Today we'll be going through the important theorems on linear independence and linear dependence. So let us start off with the first theorem. Theorem 1. So what is the theorem 1? So theorem 1 basically says that if V1 and V2 are linearly independent, then one of them is the scalar multiple of the other. So this is theorem 1, that if V1 and V2 are linearly independent, then one of them is the scalar multiple of the other. So this is theorem 1. Now let's proceed to the next theorem, which is theorem 2. So theorem 2 says us that if we have a system consisting of a single non-zero vector is always linearly independent. So if we have a system which consists of a single non-zero vector, then that system is always linearly, or the vector is always linearly independent, since it has no other vector in that system to be concerned about or be dependent onto. Now let's move on to theorem 3. Now in theorem 3 it has been said that if the vectors v1, v2, v3 up till vn of the vector space Vf are linearly independent, then none of the vectors can be a zero vector or equal to 0. So basically what they mean that if v1, v2, v3 and vn of the vector space Vf are linearly independent, then none of the vectors can be a zero vector, or that is vi is not equal to 0 where I goes from 1 to n. So this is the statement of theorem 3. Now let's move on to theorem 4. Now in theorem 4 it is said that every superset of a linearly dependent set of vectors is linearly dependent. So every superset of a linearly dependent set of vectors is also linearly dependent. This is what we mean by theorem 4. Now let's move on to the next theorem, which is theorem 5. Now theorem 5 states that let us have a vector space, suppose Vf. So this is a vector space, and then we have vectors v1, v2, v3 up till vn are vectors of v, and these vectors, that is v1, v2, v3 up till vn, are not equal to 0, or they are non-zero vectors. Then either v1, v2, v3 up till vn are linearly independent, or for some k which lies between 2 and n, for some k which lies between 2 and n, v of k is the linear combination of the previous vectors, that is v1, v2 up till vk minus 1. So this is theorem 5. So theorem 5 basically states that if we have a vector space Vf and v1, v2, v3 and v1 are vectors of B, and those vectors are non-zero vectors, then either v1, v2, v3 and vn are linearly independent, or for some vk where k lies between 2 to n is the linear combination of the previous vectors, that is v1, v2 up till v to the power vk minus 1. So this is theorem 5. Now let's move on to theorem 6. Now in theorem 6, it has been said that we have vector space Vf. This is the vector space. And then it has been said that we have a vector suppose, and we have a vector, let us take a vector suppose, what can we take? Let us take a vector w which is the linear combination of vectors v1, v2 up till v of n. Then the set of vectors v1, v2, vn and w are linearly dependent. This is the theorem 6. So theorem 6 says that if we have a vector space Vf and then we have a vector suppose w which is the linear combination of the vectors v1, v2 up till vn, then the set of vectors v1, v2, vn and also the vector w are linearly dependent. So this is theorem 6. Let's move on to theorem 7. So in theorem 7, it has been said that we have a vector space Vf. Vf is the vector space, and then we have a set of non-zero vectors. We have the vectors v1, v2, v3 up till vn are vectors of v, and v of I is not equal to 0 where I lies between 1 to n. So basically v1, v2, v3 and vn are non-zero vectors, and these vectors are and v1, v2, v3, v4 up till vn are linearly dependent. So if these vectors are linearly dependent, this is only possible if and only if one of these vectors is a linear combination of the remaining n minus 1 vectors. So theorem 7 basically states that we have the vector space Vf and then we have vectors v1, v2, v3 up till vn, and none of these vectors are equal to 0. Basically all the vectors are non-zero, and in that case the vectors v1, v2, v3 up till vn are linearly dependent if and only if one of these vectors is a linear combination of the remaining n minus 1 vectors. So if the vector Vn is the linear combination of all the other vectors from V1 to Vn minus 1, in that case the vectors V1, V2, V3 up till Vn are linearly dependent. So this is basically Theorem 7. Now let's move on to Theorem 8. Now in Theorem 8 it has been said that suppose we again have the vectors V1, V2, V3, Vn are vectors of V, and Vf is the vector space. And also V of I is not equal to 0, that means non-zero vectors. So these vectors V1, V2, V3 and Vn, now V1, V2, V3 up till Vn are linearly dependent if there is some Vk where k lies between 2 to n such that Vk is the linear combination of the preceding vectors, which are V1, V2, V3, and it goes up till Vk minus of 1. Let me repeat this theorem once again. So we have the vectors V1, V2, V3 and Vn of V, and Vf is the vector space. Now if these vectors V1, V2 and V3 are all non-zero vectors, then these vectors are linearly dependent if there is some Vk, and where Vk is basically lies between 2 to n, such that Vk is the linear combination of the preceding vectors V1, V2, V3 up till Vk minus 1. So this is Theorem 8. Now let's move on to the last theorem that we will be concerned about, that is Theorem 9. So Theorem 9 basically states that suppose let S be a linearly independent subset of a vector space, suppose V, and let beta is a vector in V which isn't in the subspace which is spanned by S. In that case then the set obtained by adjoining beta to S is linearly independent. Let me repeat this term once again. So we have a set S which is the linearly independent subset of a vector space B, and if B beta is a vector in V which isn't in the subspace which is spanned by S, then the set which is obtained by adjoining beta to S is linearly independent. So these are the 9 important theorems on linear independence and dependence. And these theorems are very important, and you need to remember these theorems to solve various questions which will come from this topic in the exam. If you have any doubts or any further clarification, or you need further questions about the linear dependence and independence of vectors, then you can comment below in the comment section and we'll get back to you. Till then, you can watch more of our videos at Solves classes for preparing for the upcoming examinations. Till then,